Hello, welcome to the final video on Year 13 Edexcel A-Levels chapter on functions. So we're about function notation now, modulus and transformations. So this last part of the chapter puts it all together and actually returns to an earlier part when we were solving problems with the modulus. So we go full circle and return to a bit earlier. So some would say the order of this chapter is slightly higgledy-piggledy, but I think it finishes quite nicely. So with that in mind, the fact that we're talking about graphs and transformations, here are some warm-up questions for you to try, all about graphs and transformations, which is current to this chapter. So pause the video now and try these questions, see how you do, and press play to hopefully see your solutions matching my own or equivalent. So assuming you've tried them, let's have a look now at the solution to question number 1. So for question number 1, we're asked to sketch on the same axes the functions f and g, which are defined as this. So we've got f of x, mod x plus 3, and g of x, which is 2x minus 1, all modded, where x is any real number. So let's get the coordinate axes here. In red, I'll do f of x, and in blue, I will do g of x. So f of x and g of x will look like the following. This is f of x. So the mod of x graph is a v shape on the origin, but we're adding 3 to all units, so the y-intercept of this one will be 3. This one here, g of x, clearly the modulus of this will be equal to 0 when 2x minus 1 equals 0. So when x is equal to a half, we're going to cross the x-axis. Then when x is less than a half, we're going to be going with a negative gradient. When x is more than a half, a positive gradient. So g of x will look something like this, with a x-intercept of 0.5, and the y-intercept, if you just plug in that x is 0, the y-intercept will be the mod of minus 1, which of course is 1. So this intercept here would be 1. And in fact, I suppose we can have this on here, so why not? We're going to use this for question 2. So using the sketch just before, we need to solve the equation mod x plus 3 equals mod of 2x minus 1. So if I just remind us of the sketch we had from earlier, with x plus 3, mod x plus 3 in red, and mod 2x minus 1 in blue, we have this. So how to solve this equation? So clearly we can use this graph, so that's okay and we can do it now, just by using the graph. So clearly there's going to be 2 solutions. The first one's going to be over here, like so. And the second solution is going to be this one here, like so. Is that line, this first line, straight? It looks a bit wonky. There we go. So clearly, if I just label this solution A here, and this solution B. So for point A, for solution A, you can hopefully see that the red line is a negative gradient. This is where the mod x plus 3 is actually having a negative gradient. So this line here is actually the line 3 minus x. So for A, that's the point where the line 3 minus x equals the blue. This one here, again, is going downwards. Before a half, this whole thing here will be negative. So we need to multiply all this by minus 1 to make it positive. So that would be where this is equal to 1 minus 2x. And for equation B, well, for solution B rather, I should say, we've got where both gradients are positive. So this section here is the graph of mod x plus 3. When an x is positive, that's just going to be x plus 3 equals 2x minus 1. So we solve these together to get the 2 points of intersection. So from the first one, if I add 2x to both sides and then subtract 3 from both sides, what I'd get there, adding 2x to both sides gives me an x over here, and then 1 minus 3 would give minus 2. So one solution here is that x equals negative 2. The other solution, what we have, is from this one here. So if I were to subtract x from both sides, that would give me 3 equals x minus 1. So the other solution, adding 1 to both sides, we can see that x would have to equal positive 4. So this one here is when x is equal to -2, and over here for b, that's when x is equal to 4, when the functions intersect. In part B of question 2, we have to solve a modulus inequality. So we need to solve a mod of 2x minus 1, where is that less than 1? So to solve inequalities involving moduluses, or moduli, I suppose I should say, using the Latin, we can always remember this following general result. So when dealing with equations of a type mod A less than B, or mod A then whatever symbol B, the solutions are given by solving when A itself is less than B, and when minus all of A is less than B. Whatever inequality symbol you've got here, keep it exactly the same and the same way round. So applying this idea to the question we need to solve here, we need to think of two scenarios. So the first scenario is when 2x minus 1 is less than 1, and the second scenario is when this all minus, so 1 minus 2x, is less than 1. So solving these two different parts. So from this one, if I add 2 to both sides, I get 2x needs to be less than 2. Then dividing by 2 both sides, x must be less than 1. Over here, if I were to add 2x to both sides, I get 1 would have to be bigger than 1 plus 2x. Take away 1 from both sides, 2x needs to be bigger than 0, so therefore x needs to be bigger than 0. And so if x needs to be less than 1, but x needs to be bigger than 0, we can now combine these to get our overall solution. So therefore, from both of these, we can see that x needs to be bigger than 0, but less than 1. So putting that into one inequality, we have x needs to be in between 0 and 1 exclusive. Now we can picture this on our diagram. Essentially, we want where 2x minus 1 all modded, the blue, is underneath the line where y equals 1. So if I were to picture this by drawing the line y equals 1, like so, essentially we're wanting the piece of the blue graph which is underneath the green. So we want this section here, or that section there. So anywhere in between 0 and 1 is where it's underneath the green line, representing where y is equal to 1 here. Question 3. For the warm-ups, we have a diagram below showing the graph of y equals g of x. We're asked to draw and label the graph of y equals gx all modded, and then also the graph of g of mod of x. So in blue, I'm going to do the graph of g of x all modded, and in red, the graph of g of mod of x. So if we take g of x and mod it, all this means is anywhere where the graph is underneath the x-axis gets reflected in the x-axis. So this here, this V shape, will be exactly the same, but where this bit here is underneath the x-axis, this will be reflected upwards like so. And so the blue line, the graph of y equals gx, will look like a W shape. And then if we remember correctly how to graph y equals g of mod x, this function here is a reflection of g of x in the y-axis, but only for the part where x is 0 or greater. So we're reflecting this bit here of g of x in the y-axis. So it's like a tick shape, so we're going to get another shape over here. So that's going to look like a very big W with its vertex here on the y-axis. So for B, the graph of g mod x will look like this. A big red W. Warm-up question 4. We have a function h defined as being h of x is e to the 0.5x plus 1. We need to find h minus 1 of x, which is the inverse of x, and we need to state its domain and range. So what I'm going to do here, first of all, is I'm just going to let h of x equal y. So I can start by saying y equals e to the 0.5x plus 1. And what I need to make here is x the subject of all of this. So if I isolate the e to the 0.5x by subtracting 1 from both sides, that will then give me that y minus 1 equals e to the 0.5x. I can then take the natural log of both sides. That will just give me what 0.5x is, and will eliminate the e. So if I take the natural log of both sides, so ln of y minus 1, that must equal the natural log of e to the 0.5x. So then ln and e essentially, for lack of a better phrase, cancel. So on the right, that will just give us 0.5x. And on the left, we have ln of y minus 1, obviously. We're not quite done. To make x a subject, I need to double both sides. So if I multiply that side by 2 and this side by 2, I can see that therefore x must equal 2 lots of the natural log of y minus 1. Then to work out the inverse, we just simply switch the letters. Instead of x, we replace this with the inverse notation, so that's h minus 1 of x, and we replace y here with the x. So h minus 1 of x equals 2 ln of x minus 1. So now we've done a few warm-up questions, we should be suitably ready and brave to have a look at this main activity here today. So solving modulus problems, take 2. So let's just do some worked examples straight off of that. We've done all the legwork, now it's just piecing it all together. So worked example 1, solving modulus problems. We have a function f of x defined as 3 lots of mod x minus 5 minus 2, where x is any real number. We need to sketch the graph of f, stating its range. So let's just build this up step by step, like we have done in previous chapters. So the f of x graph will be in red when we're finished, but we'll start from a basic parent function. So let's just get some axes on, and we'll sketch step by step. So here, we're taking the mod of something, so the parent function I would suggest we begin with is simply mod x. So the graph of mod x is just a v with its vertex on the origin. So the graph of mod x would look like this. Then remembering the order of transformations, which we've not wrote down explicitly here, we need to now focus on the minus 5 next. This minus 5 is inside the modulus symbol, which works like brackets essentially. Inside, be thinking opposite. So next we can transform to x minus 5. It looks like the common sense thing to do would be to subtract 5 from x, because it's inside the mod. It's the opposite to common sense. We're going to add 5 to all x values. So the origin here is going to move 5 along. The v vertex will be somewhere here. It's going to move 5 units to the right. So we now have this. The x-axis intercept will be 5, and the y-intercept will be 5. So labelling these on like so. X-intercept 5, y-intercept 5. Next, do we deal with a 3 or a minus 2? Well, now we're stepping outside of the mod symbols. It works as common sense BIDMAS. So we'd multiply before subtracting. So now we're going to deal with this 3. That 3 is going to triple the y values. So next, considering 3 lots of x minus 5, this v is going to be much steeper. It's going up quicker, essentially. So we're going to have something that looks like this. The y values triple, so the y-intercept will go from 5 to 15. X isn't affected, so the x-intercept will stay at 5. Final step now, I can take all of that and subtract 2 from it to arrive at f of x. That minus 2 just has the effect of subtracting 2 from all y values, so this v shape just gets shifted 2 units down, so it ends up being slightly below the x-axis. That 15 we take 2 off, which becomes 13. And we don't yet know what the x-axis intercepts are, but we can work that out in a second. We can work this out, by the way, by remembering that in general, when dealing with equations of a type mod a equals b, the solutions are given by solving a equals b and minus a equals b. So what I could do here, I suppose, is actually just add on this line. So let's imagine the line, say g of x perhaps equals half x plus 1. So that line would have a gradient of a half and would cross the y-axis at positive 1. So we're looking for something like this, we're looking for these 2 points of intersection. So by considering our graph sketches, we can hopefully see there's going to be 2 different solutions, which is going to be given by these this little hint here. And so scenario A, if we like, scenario A, this one over here, that's when x is less than 5. So obviously the vertex here was 5, that's going to be 5. When x is less than 5, f of x here, this mod symbol is going to be made different. So in fact what we can do is just isolate the modulus symbol here. To solve when f of x is equal to the green, we need to work out when 3 lots of x minus 5 minus 2 minus 2, when that equals a half x plus 1. So we can work towards isolating this modulus symbol. So first of all, I'm going to suggest we add 2 to both sides. We then get 3 lots of mod x minus 5 equals a half of an x plus 3. Then to get the mod symbol on its own, I'm now going to divide both sides by 3. And that'll give me that the mod of x minus 5 is half x divided by 3, that's 1/6 of an x. And 3 divided by 3 is plus 1. So therefore, I'm solving when x minus 5 equals 1/6 of an x plus 1. And I'm going to solve when minus this modulus, in other words, when 5 minus x equals 1/6 of an x plus 1. So for the first one, if I subtract 1/6 of an x from both sides, that gives me 5/6 of an x over here, that will disappear on this side, then add 5 to both sides, I get that 5/6 of an x equals 6. Therefore, dividing both sides by 6 and dividing by 5, I get that therefore one solution is that x equals 36 over 5. So that's one solution. The other solution will be given from this equation here. So in the same way, get the x's onto one side and the numbers onto the other. So if I add an x to both sides, 1/6 of an x plus an extra x is 7/6 of an x. And if I subtract 1 from both sides, so it'll have 4 over here, then if I then divide everything by 7 over 6, x will be 4 divided by 7/6. If you want to show it on your calculator, you can, but then you get therefore x should equal 24 over 7. So those are the 2 solutions to when f of x is equal to half x plus 1. So I suppose we could add these onto our diagram as well if you want to, so why not? So this point here is going to be 24 over 7. This one here, 36 over 5. Finally, we need to explain why f doesn't have an inverse. For a function to have an inverse, we need to recall the function must be 1 to 1. Whereas actually here, we can see that we've got 2 different x values each time going to the same y value. So this is a many to 1 function, it's not a 1 to 1. So f doesn't have an inverse simply because it's not a 1 to 1 function. Let's now have a look at work example 2. So for worked example 2, we have a new function, this time defined as g of x, which is 6 minus 2 lots of the mod of x minus 3, where x is defined as any real number. So we need to sketch the graph of g stating its range. So the graph of g, let's just get some templates ready, like so. So we're going to do the final function g in red, and here are the templates. Let's start with the parent function, which is mod x. So the graph of mod x is just a v centered on the origin. Remembering the correct order of transformations, we then need to focus on this minus 3 on the inside. So what would the function mod x minus 3 be like? This minus 3 is inside the mod symbols, So it's going to work opposite to common sense. So it looks like we're going to subtract 3 from the x values. Opposite to that common sense approach would be we're actually going to add 3. So this V shape is going to move 3 units to the right, so we have something like this. Next, do deal with the -2 or that +6. Now we step outside of the modulus symbols, it works as common sense bidmass. So we multiply by the -2 before adding the 6. So next we focus with the -2. So before we do that, just remembering the x-axis intercept here will be 3, and the y-axis intercept will be 3 here. So next, this one here, this is going to multiply this V shape by -2. So it's going to actually flip and be reflected in the x-axis because all the y values which are positive are now going to be multiplied by -2, so they're going to be negative and larger in size. So we're going to have a V shape looking like this, inverted. It now points up. So this point 3 will still remain as 3, but the y coordinate gets multiplied by -2. So 3 times -2 goes to -6. This will stay as 3, as I say. Finally, this 6 has the effect of just being added on to the -2 mod x minus 3. So finally, this 6, we just add 6 units onto y. So now we go back to the origin for the y-axis intercept. So this -6 here now goes to 0. The vertex here will now go to the point 3, 6. So that's the graph we have. So this is still at 3. And that's our graph of g of x. By symmetry as well, we can say this is 6. If that's 0 and that's 3, from 0 to 3 is a gap of 3. Then from 3 to 6 also is a gap of 3. So we can use a symmetry here of the modulus. So we've sketched it, and its range we've not given, but clearly we can see it's going to peak here when y is equal to 6. So therefore, the range of g of x is g of x must be less than or equal to 6. Next, we need to solve the inequality where g of x is greater than 4. So let's just picture this as the line y equals 4 first. So imagine the line y equals 4 in green like so. If we want g of x to be bigger than 4, we're wanting to find the critical values where this red is above the green. So remembering how to solve modulus problems, I'm just going to remind us here, we can follow this same approach. So isolate the mod, and then think about when what's in the mod is less than the other side, or minus what's in the mod is less than the other side. Whatever inequality symbol this is, just keep it exactly the same, whether less than or more than, whatever. So we're wanting g of x to be bigger than 4. So g of x is in red. So I'm wanting to find when 6 minus 2 lots of mod x minus 3, in other words g of x, is greater than 4. So I can isolate the mod symbol and then find the 2 inequalities I need to solve. So the first thing I'm going to do is to add 2 lots of mod x minus 3 to both sides. So that'll give me 6 is bigger than 4 plus 2 lots of a mod of x minus 3. If I now subtract 4 from both sides of this inequality, I get that 2 needs to be bigger than 2 lots of the modulus of x minus 3. Therefore, dividing both sides by 2, I can see that the mod of x minus 3 needs to be less than 1. I just switched these around. In other words, 1 needs to be bigger than the mod of x minus 3. So from here, we're going to have 2 different inequalities to solve. So the first one, we keep x minus 3 as is, and think when that's going to be less than or equal to 1. That's quite simple. Simply add 3 to both sides. So we're wanting x to be less than 4. The second scenario is when all of this is made negative, and that's less than 1. So the second scenario is when is 3 minus x less than 1. So if I add x to both sides, I need 1 plus x to be bigger than 3, then finally subtract 1 from both sides, I can see that x needs to be bigger than 2. So piecing these two bits together, if x needs to be bigger than 2 but less than 4, we can deduce that x must be in between 2 and 4 exclusive, I mean to say. So in terms of this graph here, all this is saying is that therefore this bit here is going to be where x is 2, and this here is going to be where x is equal to 4. And in between 2 and 4, that's when the red is higher than the green as required. Finally, another worked example. So worked example 3, this is adapted, this is an exam type example. So we've got a diagram showing the sketch of part of a graph y equals f of x shown in red, where f of x is 3 mod of x minus 4, then all of that minus 5. First of all, we need to state the range of f. Part A is fairly straightforward. It's part B that could either be fairly straightforward or very complicated indeed. So I'm going to show you two ways for B. One way is much simpler. But first of all, for part A, the range of f. I've underlined the minus 5 here. Clearly the mod of something, by its definition, needs to be at least 0. So the minimum of this bit here is 0. So f of x is going to have a minimum when x is at 4, then y will be minus 5. So this vertex here must be when y is equal to minus 5. So this red V is at least minus 5 for everything. So therefore we can say that the range of f of x is that f of x needs to be minus 5 or greater. Part B is where it gets a bit more confusing. So I'm going to show you one of two different ways to this. The first way is a standard way, the second is visual, which I'm sure you'll agree will be actually much simpler. So first of all, solving B in the standard method. So I'm wanting it where f of x equals minus a third x plus k. So let's just write this down. So f of x is 3 lots of x minus 4 minus 5. I want that to equal minus a third of an x plus k. So my first step, I'm going to try and isolate this mod here. So I'm going to get this 5 added to both sides first. So 3 lots of x minus 4 will be minus a third of an x plus k plus 5. If I now divide both sides of this equation by 3, and get that x minus 4 equals, then minus a third of an x divided by 3 will be minus a ninth of an x. So I'm going to say minus 1 over 9 of an x. Then this k plus 5, k will be divided by 3, as will 5. So I'm going to write this as k plus 5, all divided by 3. So what I can do here is realise that now we can solve x minus 4 equals this, or minus x minus 4 equals this. So therefore the two bits we're solving is when is x minus 4 equal to minus 1/9 of an x plus k plus 5 over 3. So first of all, and we need a bit more scope for this because it is a bit more complicated. So if I now add 1/9 of an x to both sides, so again I'll just clear this off like so, just make more space, I can now essentially add 4 to both sides if I wanted. But first of all I'm going to add the 1/9 x to both sides. So 1x plus an extra 9th gives me 10/9 of an x equals k plus 5 over 3, then I'll add this 4 as well. So I'm going to rewrite 10/9 of an x. Now 4 is the same as 12 thirds. So if I write 4 as 12 thirds, I can combine this into this fraction here. So k plus 5 over 3 plus 12 over 3 will be k plus 17 over 3. And so that's one solution. So that's one equation I have relating to k. Another one would be if it were actually minus the mod of this equals minus 1/9 x plus k plus 5 over 3. So the other solution will be given from 4 minus x equals minus 1/9 of an x plus k plus 5 all over 3. Now this time I'm going to add x to both sides. So x plus minus 1/9 will give me 8/9 of an x essentially. And then I can take away k plus 5 over 3 from both sides. So I have a 4, but I'm minusing that k plus 5 over 3. But again, because 4 is 12/3, I can combine this all into one fraction, so 12 over 3 minus k plus 5, that'll give me a fraction, which is 7 minus k, because that's 12 minus a 5 is a 7, all over 3 equals 8/9 of an x. So that's the second one. As you can see, this is already quite long-winded. I want to solve for the possible values of k. Okay, so what I'm wanting to do here is to find the crucial value of k that will work. So if I just think about this actual minus 1/3 of an x plus k for a moment, actually, and if we just consider the graph of this, if I put this in blue, then basically it's going to be a straight line with a gradient of minus 1/3 and a y-intercept of positive k. So this line might look something like this. So it's just a case of whereabouts, what does k need to be, the critical value of k. So as you can see here, the solution might have two roots. If this blue line was lower, it might just have one at this vertex, and this is the crucial value of k we're trying to find actually. Anything less than that, the blue wouldn't intersect the red. And so that's why we're trying to find a crucial value of k. The value of k that will actually satisfy both the blue and the red equations here will be the critical value at this point. So as long as k is bigger than that, as long as the y-intercept is higher, we will have two distinct roots. So that's just giving a bit of visualization to what's happening here. But the visual method on its own is actually much quicker, so bear with me if you're finding this quite hard going. So anyway, I've got here two simultaneous equations essentially, just to carry on. I want to find what the crucial value of k is. So I'm not interested in x at this particular time. I'm wanting what k is. So I've got 8/9 of an x on one, 10/9 of an x on the other. And so what I could do here is get basically 1/9 of an x for each equation. So if I take all of this and divide the whole thing by 8, I can, divide by 10. I don't know what I'm thinking sometimes these days. Must be old age. Or maybe it's for winter weather. So if I divide by 10, because I've got 10/9. So divide by 10 to find out 1/9 of an x is. So 1/9 of an x will be k plus 17 over 30. So that's what 1/9 of an x is. Over here, this one, I've got 8/9 of an x. So if I divide by 8 to find what just 1/9 is, 1/9 of an x will be this fraction, 7 minus k, divided by 3, then divided by another 8. Dividing by 3, then divided by 8 is the same as being all over 24. So this is 1/9 of an x, as is this, so I can set these two equal and then solve. So from these two, that line was a mistake. I can then say that k plus 17 all over 30 must equal 7 minus k all over 24. So if I now cross multiply these two together, there's other ways of solving it, but I quite like the cross multiplication way if I've got one fraction is equal to another. So k plus 17 multiplied by 24 is 24k, and 17 times 24 is 408. So 24k plus 408 equals 30 times 7, which is 210. 30 times minus k is minus 30k. If I now add 30k to both sides, I get 54k. Subtract 408 from both sides, so 210 minus 408. That gives us minus 198. Then finally, dividing by 54, I get minus 198. That looks a bit too much like 798. There we go. So minus 198 divided by 54 gives us a value of minus 11 over 3. Now this isn't quite right, in fact. What we're wanting to solve here is where we want it to have two distinct roots. So the crucial value of k, the critical value would be minus 11 thirds. But what we're actually wanting here is for k to be greater than minus 11 thirds. So if minus 11 thirds were here, k would just have one repeated root. But if it's higher, this blue would cross the red 2 times and hence give 2 distinct solutions, which is what I need. So actually, it's not a case that k will equal that. It's a case that k needs to be greater than minus 11 over 3 to obtain those 2 distinct roots as required in the question. Now, I did promise a much simpler way. Just think of it purely visually. So, just thinking of this purely visually now, let's see if we can find a much simpler way of tackling the same problem. So the visual solution begins by just imagining the line y equals minus a third of an x plus k, this line here straight away, then realizing that the number of distinct solutions is the same as how many points the functions intersect each other. So here it'd be 2 times. So the critical value, k, needs to be higher than, for example, here, where there's no solutions. Here, there's only 1. So higher than this point, this is the crucial point here that k needs to be higher than. If k is greater than that, we have 2 distinct solutions. So I'm trying to find this crucial y-axis intercept here. So using the graph and part A and what we have, we can actually conclude what k has to be by just using the graph. So f of x, like I said earlier, this is going to be minimized when x is actually equal to 4, because that's when the mod of it is going to be equal to 0. So we can actually work out that this point here is when x is equal to 4. So we can add this one in, like so. And when we also know when x is 4, y is equal to minus 5. So we know essentially the coordinates of this vertex. So I know this point here is 4 minus 5. So I can actually use some GCSE straight line geometry here. So if I think about y equals minus a third of an x plus k, but at the crucial point of k, this blue line is going to go for the point 4 minus 5. So now I can sub in 4 minus 5. In other words, when y is minus 5, at the critical value of k, this is, x is 4. So minus a third of 4 plus k. So I've got minus 5 equals minus 4 thirds plus k. In fact, I should say k critical. Or k crit, to be lazy. So therefore, k crit, the critical value of k, is going to be minus 5 plus 4 thirds. So if we try this, minus 5 plus 4 over 3, hey presto, we get minus 11 over 3. So therefore, k must be greater than minus 11 over 3, like we had before, using the much longer-winded method, but it's still valid. So I'm not saying long-winded in any disrespectful fashion. Either way, we need to arrive at k must be greater than minus 11 thirds. So now we've tried these, it's over to you to try some questions on your own. So if you were to turn to page 51 in your blue books, page 51 to 52, exercise 2G. My suggestion is just to try all questions there. So keep practicing hard. Do let me know if you're struggling in class. Find me, email me, or drop me a comment on the video. So keep going, never give up, and be in touch. So until next time, it's goodbye for myself.